Welcome everyone to the last session of ICAPS, and the session is on classical planning. We have three talks. The first paper is Potential Heuristics, Weakening Consistency Constraint by Pascal, Lauer, and Daniel Fišer, and Pascal will present.
Thanks for the introduction. So where all of this work started was that I really like looking at this very trivial planning task, which is called visit one. It's basically an adaptation of visit all, which is even simpler. We just want to move across this grid and get to some final destination. And if we would encode this in an FDR planning task, it would look like on the right-hand side, we have one variable to denote the position of the player and one variable each to denote if some spot was visited or not. Then we can move across the grid, mark the positions visited, and in the end, we want the goal to be at this final position. So just pro forma, like the wording I use is like a variable assignment is called effect, and state is just a set of facts of different variables, and then S denotes the set of states. A heuristic is a mapping from states to a value, and we say a heuristic is goal aware if for every state that contains the goal, we get a heuristic estimate that's less or equal than 0. It's consistent if in every state transition we under the decrease of our heuristic value is less or equal than the cost of the operator, and it's admissible if we underestimate or get the exact same estimate as the perfect heuristic. And we know that the heuristic is admissible if it's consistent and goal aware. So just to put this out there, like in the paper, what we analyze depends on some forward reachability properties. So strictly speaking, I would have to speak about forward admissibility and all that stuff to make it easier for myself. I will just say admissibility. Okay, so what's a potential heuristic? A potential heuristic assigns a value to each fact in the state and then simply sums up these values. And if we would want to derive these potential values, we kind of want to give them some kind of sense, right? We could assign any values, but rather we would like them to make sense and be a useful heuristic, and for that we want to ensure exactly these heuristic properties I've just shown you. What we want to ensure is basically the consistency property. This would be very easy if for every operator we would have that the preconditions supersede the effect. So for every variable in the effect, we will find the precondition, because then we could just distract the values from precondition and effect. But that's obviously not always the case, so we need to find some overestimation, and what we can do is just to maximize over the values for the variables that are not in the precondition. I will use a bit more concise notation for this. So basically these disambiguation maps are mapping a variable to all the facts in the case if it doesn't occur in the precondition, and to just one fact if it did. Strictly speaking, it's a bit smarter. So like this is from related work. It doesn't try to always consider all the values depending on the precondition of the operator. We can also prune some additional values when I've just shown you. Like that we would maximize over the entire domain, but again, that's related work, previous work, we can just reuse it. And then how we can encode these constraints is basically to maximize over the disambiguations for all variables to achieve goal awareness and do the thing I've just shown you for consistency. Okay. So if you would want to encode a potential heuristic, so the potential function mapping the facts to values for the task I've shown you, what we could do is to get to an almost perfect heuristic, which means we get the exact perfect heuristic estimate for all states that derive a value greater than 0 and otherwise a negative value if we would use this. So we assign the potential value as a Manhattan distance and then kind of punish the previous values by assigning a -4 to the goal, which is the maximal distance. So now if we look at the task and we move across the task, what happens as we are getting closer to the goal, we're exactly experiencing this Manhattan distance, which is the perfect estimate, and we do the final transition, and we get a heuristic value of -4. This is kind of cool in the sense that we have a admissible heuristic, which is almost perfect. The problem is that this very last transition is inconsistent. And I told you before that we want to ensure consistency. So if we would try to derive a potential heuristic this way, we would never be able to get to this heuristic function. And just for completeness, obviously, if this happens in the original state transitions, if we would put in the values for our constraint, it would lead to the same problem. We could not find this potential function. And in fact, it's even worse than that. We cannot just find, it's not just not finding a perfect function. What you can actually prove is that all potential functions you derive for the constraint I've shown you are bounded so that your initial heuristic value will be at most 2 independent of the grid size. So by the construction that we would want to create, we could get the perfect heuristic, but in reality, what people have done so far would be bounded by 2, which is not a good heuristic at all. And now you could tell me that this is kind of stupid, right? I'm showing you this grid and some player that moves from the initial state to the goal. Who cares about that? Like, the heuristic will be for sure better on the IPC benchmarks or whatever. But I'm telling you, like, this very gimmicky task actually contains properties that occur in many other benchmarks. And examples for this are logistics. So basically, what we are capturing here is some distance between something we want to achieve in the end, and there's some distance in between. And we can observe the exact same thing in logistics. When we want to pick up a package, deliver it somewhere and place it, so move to a destination and place it somewhere. That's the exact same distance, and actually in the paper we don't use the visit one task but the logistics one. And another domain where the exact same thing happens, again because we have these distance properties and we want to get in somewhere and out somewhere, is the elevators domain, where we get in, travel through levels, have this distance, and get out. Okay, so what can we do to address this problem? And kind of there's already a solution out there, because actually if you look at planners, what they would do is not just consider the potential heuristic, but because searches typically dislike negative values for heuristics, what they would do is wrap the potential estimate and maximize it with 0. So if we check this again in the state transition, suddenly this state transition will only decrease by 1, and we are consistent. The same holds. Sorry, it's below. On the bottom line, no. Sorry, I could spare I added a slide that also shows this for our original constraint. So I guess you just have to trust me that it should. Wait. Oh, sorry. Okay. Let me start again. So we know that in the state transition system, we are now consistent. And we want to derive a constraint which would be able to capture this. So exactly this maximization. And so what we would do is to plug in just the new heuristic function, which maximizes over the original potential value and 0 into our consistency constraints. And kind of, if you play around with the equations, what you can get to is this minimization of our original old constraint for consistency and something else we still need to derive an estimate for. And if you understood how the goal constraint works, this is very similar. So kind of what we are trying to estimate here is that we know a certain part of the precondition holds, and we just maximize over the disambiguation maps we can infer with respect to the precondition. So now we can revisit the example with the new consistency constraint, and we will see that if you would input all values, we would be consistent with the new constraint. And how we would actually realize this is that we would use an ILP instead of the usual LP formulation for potential heuristic, and then we can kind of encode a switch to choose either one of the formulations. And the nice thing about this is that we reuse the old constraints, so like the values can just get better, but the problem kind of is that we use an IP which can be slower to solve, right? So we should have a look at what actually happens in practice. And on the left-hand side, what you can see is exactly what I've told you, like the P plus I configuration is our new constraints, and the PI, the usual potential heuristic constraints. And on the very left, these dots that are basically a constant and then walking upwards are showing exactly the behavior I showed you in theory in the beginning, where you have like a constantly bounded heuristic value, and then now it scales linearly. The thing is that there's a kind of a bit of a difference between practice and theory. We are a bit bottlenecked by the time the IP solver takes. So if you look on the right-hand side, this is basically if we didn't say we want to solve the ILP optimally, but within some short time window. And there we can see that we can reach a lot better heuristic values, but we can no longer guarantee that we are better than the original potential formulation. Another metric we could use is the famous coverage table. So what we compare here are the configurations P, P plus, and POR, which mean original potentials formulation with the indicator constraints, and a portfolio which first runs P, then this usually finishes within like 5 or 10 minutes or exhausts the memory limit, and then we can use P plus. And for optimizing the initial state heuristic values, so the first column, this improves a lot in coverage, so it really makes a significant difference. But for the more competitive variants and other optimization values, so the average state, we need the portfolio to be a bit in a few tasks. And I think kind of the mission here would be to figure out why the increase in heuristic value and the coverage don't necessarily correlate as much. So a mission for future work. Thank you for your attention.
Thank you. We have lots of time for questions. Malte.
So I don't want to excite too much of the example, but let me do it anyway. So part of the issue here is that the goal is formulated in terms of having visited the cell, than being at that cell. So that makes half of the state space a goal state.
Yes.
And that's quite frequently a problem, right? That there's so many goal states because the heuristic values all have to be less or equal to 0. But you could sort of try to infer, well, the first time I reach a goal state, other things have to be true. Like the first time this cell becomes visited, I have to be at that location, right? Mm-hmm. So have you thought about techniques that sort of try to be a bit more, let's say, restrictive in that regard, sort of reasoning a bit more about the goal than the disambiguation already do?
I've thought about it, but I've not come to a solution. So like I had the same thought, but once you have two sets you need to visit, it becomes quite tricky. So yeah, it's a nice idea if you approach me offline, if you have more ideas in that direction, but
we can kill this, but beyond that, who knows?
Yeah.
Let's talk.
Okay, any other questions? So I have one maybe while you're thinking about your next question. So the atomic potential heuristics are bounded from above by the state equation heuristic. Mm-hmm. Do you have an idea of what these heuristics are bounded above and how close they are? Like how close to the optimum do you get with this kind of optimization?
Yeah, I think like the question basically relates to this, right? So if we would, so first of all, I have no idea so far, but it's something I wanted to look at because I can imagine that basically the difference with this is that the state equation equivalent, so like evaluating like this formulation on every state, optimizing for the current state, could make a huge difference to the average state, and this would also explain the difference in coverage. But I simply didn't have the time to look at this yet.
Yeah. Cool. Any more questions? Yeah, I have one more maybe. So you said that like maybe can you go back one slide to the plot? Yeah, exactly. Like these where you can't finish the optimization, you get lower heuristic values than just optimizing this. Would it help there to like first optimize the original formulation of the potential heuristic and then like start the solver from that solution? Would that guarantee that you always get a dominating solution?
It would guarantee it. Yeah, but we tried this, and I don't understand why, but once we do it, we basically end up at the left-hand side and don't get all the nice dots with a huge increase in heuristic value anymore. So there must be something inside the solvers that if you kind of let them operate all on their own, that allows them to solve these, get to these better solutions, and I don't get why.
Interesting, yeah. Cool. So, any more questions? Then let's thank the speaker again.